Okay, so shall I start? All right, well, thanks to Kedar and Subroto for organizing a very nice meeting, and nice to be back in Bangalore. So I'm going to talk about some theoretical and experimental work on the cuprate superconductors. This is in collaboration with a number of people, including Debanjan, who's here in the audience, and various students and postdocs at Harvard, some of whom are no longer at Harvard. I'm actually going to begin by talking about some experimental results in collaboration with the group of Seamus Davis at Cornell. Okay, so that's just to have a very gentle introduction to cuprate physics, although it's going to speed up fairly soon, I guess. High temperature superconductivity is a phenomenon in compounds like yttrium barium copper oxide, where all the action is in a square lattice of copper and oxygen ions. And at certain values of x, you have a state which is an antiferromagnet sitting on the copper sites. And then as you vary x, some of the copper sites lose their holes, lose their electrons, and so you get these holes, and we assume there's a density P of holes. So now the question really is what happens as you increase the density P at 0 temperature. You start with the antiferromagnet. We know that in the experiment you end up with a high temperature superconductor, and we want to know how that evolution occurs. So one thing I should note right away, which will be important for many of the things I'll discuss, is that when we measure the density of holes, we're doing something unconventional. We're not doing what you do in semiconductor physics. If this was semiconductor physics and band theory, the density of holes here is actually 1 plus P, not P, because in band theory, you're always measuring with respect to a filled band. So in a filled band, you could put 2 electrons on each site. So really, there's also 1 hole on every site of the opposite spin, in addition to the extra holes that I've shown. So in terms of band theory, the density of holes is 1 plus P. But relative to the insulating antiferromagnet, we conventionally refer to that. The density of holes is P. Okay, so as a function of P, this is, there's a dark line here that's missing, okay, because of the colors. This is the kind of phase diagram. Here's the antiferromagnet, and once P is large enough, you have a D-wave superconductor. And then you also have this boundary, which is not showing up because of the colors here. I'm sorry. You see part of it here, but it continues up here at a temperature called T star. And really the focus of my discussion today will be what is this PG, what's happening here at low doping. So first, let's quickly review some very basic things. So in the antiferromagnet, which is insulating, there's a very small density of holes which are pretty much localized. You have this checkerboard arrangement of up-down spins. Then we also know that out here you have a beautiful D-wave superconductor with a high TC, and this has also been very well established in numerous experiments. But if I now turn to the metallic states above TC, then out here you get a Fermi liquid state where if you look at the area enclosed by the Fermi surface in photoemission, that indeed is 1 plus P. So this is a state that you would say is very well described by band theory. If you just did band theory, you would get exactly this Fermi surface, and indeed you do, has the right area, and so on. So if you were sitting over here, a Fermi liquid approach would be the right way to begin, in principle, and maybe that would be the way you want to understand D-wave superconductivity, and many people, of course, have tried, with some success, methods of that type. But the most mysterious thing about this phase diagram is really what's happening here over a fairly wide range of temperatures, and you, again, can't see that boundary. And if you do photoemission, instead of seeing this very beautiful, well-formed Fermi surface everywhere, what you see is something rather mysterious. You see intensity on what are called arcs in certain regions of the Brillouin zone, which are also temperature dependent in some way. And really, one of the big questions is what is this state here, which is, if you look at transport properties, especially in some recent work, it looks like a Fermi liquid. Some of its resistivity and optical properties are similar to that of a Fermi liquid, but with a density of carriers of P naught 1 plus P. Okay. Then the recent advances in the last 3 or 4 years have been looking at the structure of the pseudogap phase at low temperatures. There's been a lot of work on that, and especially the lanthanum and the stripe compounds, if you wish. But now in VSCO and YBCO and the highest TC compounds, there is very good evidence of some sort of ordering, which I'll just, at the moment, I just refer to as density wave in this region over here. So in the first part of my talk, I'm going to just focus on what is this ordering. Just it's a purely empirical question of what's seen in the experiments, and then try to say something about the theory, what it implies for the theory. So that's sort of the basic questions here. And there's 2 features of the pseudogap, the high temperature feature and these Fermi-arc spectra, and this ordering now seen very clearly in essentially all of the compounds. And what is the relationship between them, if any, and what is the state at high temperature? So I'm going to give you a few opinions on these questions. Okay, so I mean, you can also, that many people have thought about this in many different ways, and there's a whole spectrum of how you think about it, but it's convenient to kind of divide them into 2 broad classes. So one point of view would be, well, you look at all the ordering. So there's density wave ordering, there's superconductivity, there's antiferromagnetism, and then you work up a theory of thermal fluctuations of some combination of these orders. And that's really all you need to do to understand the pseudogap. So, well, maybe that's point A. The other kind of somewhat diametrically opposed, but there is kind of a continuum between them, is very different, where you think of, you really start with the idea that there's a new type of metal, which is a quantum state, which in principle could be stable even at 0 temperature. And that quantum state leads to, at low temperatures, to instabilities which are telling you something about it. So in this talk, I'm going to take mainly this point of view, although we have in other works taken the other point of view too. All right, so but let me begin with a somewhat less controversial part, but just on the low temperature data, what is this density wave order? So again, there's been many experiments, X-ray scattering, STM, NMR, sound velocity, and I forget, I'm sure I'm forgetting quite a few. I can't possibly review all of them, so I'm just going to focus on the one I know best, and really the one that's intuitively the simplest. So, and it really goes back to understanding what these pictures mean. So these are scanning tunneling microscopy pictures of some kind of ordering on the copper-oxygen plane. The spacing between those dots is roughly the spacing between the copper sites. And these patterns have been around for about 7 years. And it does involve some analysis to get this pattern from the STM data. But the methods that I'll describe now, show an ordering pattern which is relatively independent of all those analysis methods. But there is you have to look at a certain regime of energies, and you have to get rid of certain systematic corrections, but I think those are pretty well in control. So ignoring all of that, let's just ask the question, kind of a dead image processing question. What is the pattern that we're seeing in this image? So if you look at this for a while, and you can sort of see there's something happening at a period of 4 lattice spacings. And it looks very disordered. So you would say, well, maybe this is really a charge density wave with a period of 4 lattice spacings, and it's extremely disordered. And charge density waves running this way and that way. These are the X and Y directions. And that's the end of story. And that's pretty much what everyone assumed for 7 years. And that's correct, but it's not the complete story. So that's sort of what I want to talk about in the first part of my talk. So you can forget physics. This is really a computer science question at this point. What is, or a mathematics question? What is in this image? Okay, but it does help to know some physics. So let me try to describe, how we propose to describe it. So as I mentioned, this is some kind of density wave, but you have information not only on the copper sites but everywhere in between them. And the resolution of the STM is, you have over 10 pixels on the spacing between two copper sites. So it's very, very precise resolution, which is very stable. So you want to really be able to think of a somewhat more precise quantity than the density. And the thing that turns out to be very useful is to take a density operator, which would be C dagger C at the same point R1, and split it into 2 points. So this is an observable which is, annihilates a particle at point R2 and creates it at point R1. So this is sort of analogous to when you talk about Cooper pairs. When S-wave superconductors, you have 2 Cooper pairs on the same site, but if you want to have Cooper pairs non-zero angular momentum, you separate the 2 points. So here, this is sort of an exciton, if you wish, at non-zero angular momentum. Yeah. Yeah. So that's ignore that. That has to do. I forgot now. I think that's some surface reconstruction. Oh no, actually not a surface. It's a reconstruction of the Biscoe system, which once you take Fourier transform, it completely disappears. And there are other systems that don't have it, where all the same things happen. So. Okay, so what we're going to do is to take this simple density, non-local density operator, if you wish, and write it in the following way. So you want to, first of all, have a contribution that oscillates with the wave vector q. So this is the wave vector of some charge density wave. And the important thing is to write this as the average of the 2 coordinates. And this trivial little thing was what essentially nobody did in 15 years of work on this problem, and that leads to a lot of confusion. But I think this is in fact the right way to do it. Then this constant here is just some order parameter, which would be constant. So in a perfect charge density wave, this would be 1 everywhere. And what I want to focus on is this thing that depends on relative coordinate. So you have an electron on a hole, and I want to know the internal wave function. So I take P of R and write it in Fourier space. And the advantage of doing this decomposition here with the average coordinate is that the action of time reversal symmetry on P of K is very simple. Just an even function of K, and then you have preserved time reversal. So I assume you preserve time reversal because the experiment is not sensitive to things that break time reversal anyway. And so you can then take P of K and expand it in this way. I'm sorry, the colors are not coming out too well. So there's 3 components here, S, S prime, and D. And of course, you can add more, but this is really all you need. And these are all even functions, and they're periodic in the Brillouin zone. And so now I have a generalized charge density wave, or an unconventional charge density wave, which has just 1 amplitude. It has 3 amplitudes for the S component, the S prime component, and the D component. Now, when you talk about pairing and superconductivity, you only have 1 of these components. But here, it's a little more subtle because you have a Q which picks a direction. So in general, these components will mix. It won't be just 1 of them. And the surprise, as you'll see, that in fact in the experiment, it is just 1 of them. It dominates, although the others are not exactly 0. All right, so what are these 3 different types that we're going to try to mix together? So it's useful to draw some pictures. So let me just take P is equal to 1. That's a purely S form factor. Then if I take this quantity Pij on the copper sites, I and j here always on the copper sites, then this thing is non-zero if you do these integrals only when I equals j. Because this integral vanishes when P is a constant unless I equals j. So this is only non-zero on exactly the copper site. So this is what you'd call a site density wave. And I've shown a period 4 structure, although Q can be anything, and it's running in that way. So that's what we call a charge density wave. So how about S prime? with S prime, you have cosine kx and cosine ky. When you now work out these integrals, they're non-zero only on the nearest neighbor on when I and j are nearest neighbors. So what they're really telling you is something about the space between them, the bond. So this is really a bond density wave, and this is sort of what it will look like. So you have some modulation on the bonds. Now you would say, what do you mean by charge density in the bond? Well, if you're a one-band person, that's the kinetic energy of the electron on that bond. If you're a three-band person, you say that literally is the charge density on the oxygen site. So you'd have to go in and measure the oxygen site, which sits between the coppers. And this is then telling you about the modulation on the oxygen sites. So that's what the S prime is. It's a bond density wave. And you can combine S and S prime with some relative amplitude. Here I've taken amplitude 1/2. And none of this matters on Q being commensurate. Q could be incommensurate or anything else. The distinction is still there. And this would be sort of what you would get. Now, if you know a little bit about stripe physics, which I haven't reviewed for lack of time, this is the kind of pattern you would expect if you just wrote down a stripe with these antiphase domain walls of antiferromagnets and drew in the exchange energies. These are the kind of patterns you'll get. So the old stripe physics, you would say from this language, somewhat more precise language, is predominantly S and S prime. And in fact, there is a very recent X-ray scattering experiment by Dave Hawthorne by doing very clever polarized X-ray scattering in different directions. He can read off the S and the S prime components and also the D component, which I'll come to, and in the lanthanum compounds, which have magnetic order, which have a phase diagram that's somewhat different. And so seem, I think are somewhat different. EC is a predominant S prime component. So that seems quite consistent. All right. So what we predicted a few years ago, and as you'll see by the end of the talk, perhaps not for exactly the right reasons, but nevertheless we said it should be there, that the dominance story should actually be the D component. So what is the D component? Well, the D component is, again, very simple to understand if you think about the S component here, S prime. The S prime here had cosine kx and cosine ky. What you do is just flip the sign of that. So the way you think about it, you just say, look at the charge density on the oxygen sites. There's two types of oxygen sites. There's the oxygen sites on the horizontal bonds, and then there's the oxygen sites on the vertical bonds. Okay. And there's a wave on the horizontal bonds and a wave on the vertical bonds, all both running with the same wave vector in the same direction. And the D form factor density wave is one which is a phase shift of pi between this density wave and that density wave. That's quite a subtle thing. It doesn't mean that this density here is a negative of the density there. It's close to, but not exactly the negative, because you're really at a different position by half a lattice spacing. And this factor will be a little different here and here. So there's precisely a phase shift of pi between the horizontal components and the vertical components. And that's what this very bizarre density wave is. And now if you make it commensurate, your eyes can kind of stare at this and see, yes, I can understand this pattern. Is these rectangles rotating back and forth? Or you have the horizontal density wave and the vertical density wave, and they're always exactly phase shift of pi as you go along this way or that way. But if I drew this for an incommensurate Q, which I can draw, and again, unfortunately, the colors are not fully showing, your eyes can't really tell what's going on. It's a mess. Okay. So anyway, this is a more precise way of talking about what the density modulations are, accounting, if you wish, of both the copper and oxygen sites, and really looking at the intra-unit cell structure. All right, so now the question is what's happening in the experiment, and so now I'll talk about the results in this paper, which just came out last year, where I suggested the SDM data that was sitting around mostly for quite a few years, how you should analyze it. So let's go back to the same data. And really what you need to do now is to separate out different components of the density wave. So what we're going to do is take this picture and then make 2 copies of it. So these are 2 copies of the same picture. And then we're going to put a mask on them, but we're going to put a different mask here from the mask there. Here we're going to put a mask that shows you only the horizontal bonds. And there we're going to put a mask that shows you only the vertical bonds. So X and Y go this way. So these are different subsets of the same picture. And you can also put a mask that shows you only the copper sites. So you can put different masks. You're putting out different sites, different intra-unit cell structure. And the resolution is precise enough that you can do that now over rather large sample view. OK, now you might be surprised that putting a mask, you're going to get more information. But what you're effectively doing by putting a mask is taking high frequency information and aliasating down to low frequency. That's sort of what happens in radio. So there is a lot of high frequency information that you were throwing out when you just took a naive Fourier transform. By putting these masks and cutoffs, you're actually getting more information because you're doing this aliasing process. Anyway, so now you take the Fourier transform of this picture and the Fourier transform of that picture. So these are the Fourier transform of the X oxygens and the Y oxygens. And sorry, the colors are somehow not coming out very well. You have 2 complex numbers at each wave vector Q. So these are the Fourier transform, real and imaginary part of the X oxygen Fourier transform, the real and imaginary part of the Y oxygen Fourier transform. Now, you can't see this very well, but believe me that the important signal here is this peak here and 4 copies of it, roughly at a wave vector 2 pi times 1/4 0. So this means there's a density wave at 1/4 with a wavelength of 4 lattice spacings, as I said earlier, just as we knew, of course, very well. And it's a very short correlation, and the correlation in the density wave is barely 1 wavelength. So it's not very long range. And if you look at the signal here, it's very random, and you can see the colors. Its phase seems to shift very randomly from point to point. And similarly with the signal of the Y waves. So what this tells you is that you got little density waves, some running this way, some running that way, with a coherence of about a wavelength. And otherwise, it's extremely random. OK? Right? P, OK, this is around 0.1, if I remember. This has been done over a range of doping. I'll show you. I think I have a slide with what happens as a function of P shortly. Actually, I may not, but it's coming out in a paper shortly. So it's best formed around 0.1, 0.12. OK. But there's some very beautiful signal here, which is the following. So let me just pick one little pixel. There's, I don't know, 50 pixels in there in that circle. Let me pick 1 pixel of the Fourier transform of the X bond. So that pixel in the complex plane, say, sits here. So that's telling me, if I look at the X oxygens, they have a charge density wave on the average, which has that amplitude and phase. Now, if I take the same pixel, that's the crucial thing, it's exactly the same pixel, and look at the Y oxygen, then that is over there. So what you see, that's quite surprisingly, I guess, that it has roughly the same amplitude and phase shift of pi. So now I pick another pixel nearby, and it randomly has a different phase and amplitude. And that's because you have all these little patches of the charge density wave, and when you take a slightly different wavelength, they add up with random phases, and so you get an overall average amplitude that's all over the map as you change Q even a little bit. Even though the overall amplitude is large, the phase goes random. But if you stay at the same pixel and look at the Y bond, that's right there. So this is telling you that even though little patches are random relative to each other, within a patch, there's a essentially perfect phase shift of pi between the X and the Y bonds. And one wavelength is, well, is big. Correlation length of one wavelength is plenty large enough to see this. And so now, in fact, that's almost perfect at every pixel inside that circle. So these are the pairs of points inside those circles, and there's a perfect phase shift of pi. Almost not exactly, but pretty close. So now this type of analysis now you can carry out more quantitatively. These pictures are beautiful. I mean, of course, when these came out the first time they analyzed the data, and I was sure there was a mistake. How could it be so good? Well, one way you know it's so good is that if you go outside that little circle. So if you go back here, in this data, if you go outside this little circle, you look over here or anywhere else, you don't see it. It's just random. There's no correlation between the x and y. All right, so that's sort of the answer then. Now this is as a function of wave vector at a certain energy. There's also data I'll show shortly as a function of energy of the tunneling current. And if you look at the wave vector at which there's a density wave, with a factor of 5 or even greater, this is the integral of these things right here. The dominant component is the d component, which is OX minus OY. And the S prime and the S components are negligibly small. So it's predominantly just a d form factor density wave. Okay, so that's what this picture is showing. And with the benefit of hindsight, now you can look at this picture and actually see, yes, of course, that was obvious. So if you take a little piece of this picture, let me take that little piece, rotate it by 45 degrees, and zoom in. So this is, in fact, a picture that was published in 2007 by Seamus Davis's group. The plus signs are the copper sites, and these are the pixels of their STM current of the density module of what they call an R map. It's not precisely the density. And these are the pictures I was drawing. So this is a dense S and S prime form factor density wave. And I've drawn it with exactly the same scale, because then there's 6 copper sites here and 6 copper sites there. Okay, is this exactly the same thing? Well, looks like there's a period 4. There's this dark part here, but really the details don't match at all. But if I draw the d form factor density wave, you can just see with your eyes that these are exactly the same thing. You agree? Well, maybe not. To convince you, let me draw a black line across every blue line here. So take every blue line on this and draw a black line across it. It's just matching the pattern. So if I do that, you can see these are identical, really. There's a black line here and a black line there, and horizontal black lines here. That's here, and so on. So, and you see this everywhere in many different samples, many different dopings. This has been published and sitting around. These patterns have been there for a long time. And now it's very clear what they are. It's this d form factor density wave. Okay, so, yeah, this is what I promised. So this is as a function of energy. You can measure at the tunneling current. You can measure the S, S prime, and D components. And what you find is that at lower energies, where in fact these peaks disperse. These are the QPI peaks that you may know about, by which people have measured the dispersion spectrum of the Bogoliubov quasiparticles. So if you look at these quasiparticle peaks which disperse, they're actually predominantly S or S prime. They don't have this D component. But then at higher energies, in the pseudogap energy, in fact, there's a dispersionless peak, which is almost perfectly D. And in fact, the maximum of D is precisely at the pseudogap. So this is closely connected to the pseudogap, defined in other ways, and the density wave order, and it's predominantly this D form factor density wave. Okay, so then I can take this phase diagram and claim that what's in here is this kind of density wave. It's a very peculiar kind of density wave, which has a period 4, but has this angular momentum, which is d, between the particle-hole pairs. At least if you think in terms of the copper sites, a one-band model. If you think in terms of the oxygen sites, it's telling you that the X oxygens have a phase shift of pi with respect to the Y oxygens. Okay, so that's the reliable part of this talk. Well, no, but any questions so far? So that was just describing data analysis of experimental data. And it's very clear that all this data sitting around has a huge signal in it, and that signal was this phase shift of pi between the X and Y oxygens. And you can see it very clearly, even though the systems are very disordered. There's X-ray scattering. In X-ray scattering, YBCO has been done, and it's been a little more complicated for reasons I don't fully understand to get the X-ray scattering on YBCO as opposed to LBCO. But the latest I've heard from Damascelli and others who've been doing it, although the preprint has not been updated on the archive yet, they also see predominantly D form factor in YBCO. There's no STM on YBCO. Yeah. Well, that's a good question. I mean, this is relatively weak and disordered order. So clearly this order should, as you said, change the quasi-particle spectrum too. That hasn't been seen in our, there are some claims that there is some density wave or stripe effect in RPS by ZX Shen. But in any case, the D form factor won't affect the RPS response very much. It's not, for many experimental consequences, that the fact that it's D is not that important. But for us theorists, at least for us, we think it's quite interesting because it really puts some constraints on the theory. Now, another important consequence, presumed consequence of this order is that in a high magnetic field, you see quantum oscillations with presumably an electron pocket. And the hypothesis that's related to this order. But that hasn't been directly proven yet because there is no measurement in high magnetic field yet, but they're coming. Okay. So now I'm going to turn gears and talk about the high temperature pseudogap, the metal, before you get this density order. I'm going to go up here. So here, okay, we've tried various models, but let me give you a very simple picture, which I find very appealing of what I think is going on. So here's the picture I started with of a doped antiferromagnet with a perfect antiferromagnet and a few holes. But now we are in a regime where there's no antiferromagnetism, especially in YBCO and all these materials. The antiferromagnetic order has long disappeared. And so, so one hypothesis has been around for a long time, going back to people like Bhaskaran and others, is that you're in a spin liquid. So what is a spin liquid? Since this question came up earlier, it's basically the electrons, pairs of electrons on nearest neighbor sites here, forming a spin singlet. So you can do this in many different ways, and here's one particular pairing of the electrons and spin singlets and these holes. So what are the key properties of this spin liquid here, this doped spin liquid? So one property is that these dimers, or these spin singlets, can resonate with each other like that, just as in benzene. And that resonance, we now know in more sophisticated language, is described by an emergent gauge field. Depending on the details, it could be a different gauge field, but that's, loosely speaking, is the answer. So the spin liquid is characterized by the presence of an emergent gauge field, and Senthil, of course, talked about photons in 3 dimensions, and here in this particular model also you can get photons in 2 dimensions. So you have an emergent gauge field associated with the resonance of the dimers. The other important feature is that this hole can move, but it only moves by sort of a correlated move with respect to the gauge field, like that. And what that means is that, first of all, that this hole carries a gauge charge, which is the charge of the emergent gauge field describing the resonance of the dimers. Secondly, this hole, as it's moving, you can see no spin was moving, so it's spinless. And it also has physical electromagnetic charge of plus E, because there's an absence of an electron there. And when it moves, it's moving charge plus E. So it's important not to confuse this gauge charge with the physical electromagnetic charge. This is an emergent gauge field sitting inside the sample. This is the physical charge of ordinary electromagnetism. So that's the picture of a doped spin liquid, very old, of spinless holons moving around in the background of an emergent gauge field. You notice I haven't said what the statistics of the holons are. And as Senthil explained so beautifully, there are many different possibilities for this, what the statistics you assign to this. But fortunately for what I'm going to talk about, that I don't need that information. So I'll just be ambiguous. OK. Now, this spin liquid can have excitations that carry physical spin. So then I have to break a bond. I have to break a bond and get a free spin I have here. So these are called spinons. And these spinons can also move around. And when they move, they carry spin. They carry spin a half. And so these are, yikes, this is not gauge neutral. This is, okay, so it carries spin a half. And just like the holon, they carry gauge charge. So they're gauge charged. Sorry, that's a typo. That's not gauge neutral. Unfortunately, that's really crucial. They're gauge charged. They carry spin a half. And they're electromagnetically neutral. And they call, in this case, they have some excitation. They're above, they're not in the ground state wave function, but they're some excitations of the system. OK, so that's the old spin liquid picture. And it really doesn't work in describing the experiment because there is no Fermi surface at all, even on an arc in the system, because there's a gap to either the holon or the spinon. So there's a gap to the physical quasi-particle. So there's no zero energy excitation here, which has the quantum numbers of an electron. OK. So we want to add one little twist on this. And the twist we want to add is that you notice that when a holon and a spinon are next to each other, they can exchange places quite easily. And this will lower the energy. This is very loosely speaking. So they could imagine they can form a bound state. So the holon and spinon can form a bound state. And so I'll draw that bound state by this green rectangle with a spin a half sitting in the middle, just to be democratic. And this, OK. So this bound state can now start moving around. So now I have so I take every holon and imagine it does that, because it pays the energy to create a spinon and binds to form a bound state. So all the holons disappears, and I only have this green bound states between a holon and a spinon. So now I ask, what does this guy do? Well, this guy can also move around just as usual. And as it's moving around, you can see it carries charge E, and it carries spin a half. And so that's exactly the quantum numbers of an electron. So it might seem to you I've done a lot of work for nothing. I talked about all this fancy spin charge separation, but then I bound them again. So why did I bother to go through this long route? Well, but one thing I didn't do, and that's really the key point, the resonance of the dimers is still there. The dimers are still there, the blue dimers, and they can still resonate with each other. So I still have the emergent gauge field. I haven't gotten rid of the emergent gauge fields. So that's why, in some sense, this is a new state of matter. It's not a Fermi liquid. It's what we call a fractionalized Fermi liquid. Because although it has electron-like quasi-particles, it also has an emergent gauge field, or topological order. And the other difference from an emergent gauge, from a Fermi liquid, that the density of these electron-like particles is not 1 plus p, as it would be in a band theory, but p. And that's kind of obvious, because that's the number of holons you had. So that's a very naive and simple picture of what we are proposing is in the pseudogap metal. It's got a Fermi surface of area p of these electron-like objects, but it also has topological order. So it has, like, it's somewhere in between a spin liquid and a Fermi liquid. It has characteristics of both. And there are some rather deep reasons where these are connected, which I won't go into, that once you violate the Luttinger theorem, in a metal, if you have a metal and you violate the Luttinger theorem, then you must have the gauge field. I believe there's no other way to do it. OK, so what we've done recently with Matthias Punk and Andrea L.A. is to take this very simple picture and make it into an actual model. So we're going to introduce what we call a quantum dimer model, where the Hilbert space is what you see on the board. So the Hilbert space is a set of dimer packings on the square lattice. So you take for every dimer packing, you have many different states, but you pick a dimer packing. Then you color P of the dimers green, that's where your fermions are. So I should have also mentioned these. It's clear, independent of the statistics of the holon and spinon, this object is a fermion. So that's important. I mean, that's all we need. So you color some P of them, density P of them green, and then you assign half of the green dimer spin up and the other half spin down. So that's your Hilbert space. It's larger than the Hilbert space of dimer packing because of your choice of coloring and the choice of spin. But you still have very importantly, you still have all these constraints from dimer packing, which in a more formal language means you still have the gauge field. Yeah. Well, so the number of spin-ons is not conserved. You can always create as many spin-ons you want. You could also have more exotic things going on with the spin-ons. But every holon, the number of holons is fixed as P, and every holon decides it can be better off if it just creates a spin-on, pays the energy to create a spin-on, and becomes an electron again. So that's the assumption, that there is a bound state. And we ignore and that bound state will be gauge neutral. In this dimer model, it's a gauge neutral because it's sitting on the dimer, really. So that's really the key difference from, many people looked at dope dimer models over the years, but no one put the charge on the bond. Yeah, yes, now, it's an assumption if you wish. That's the model. Of course, we have more sophisticated field theoretical models where we can justify things, but then it's hard to really calculate much with it. So this one, we just make a postulate, but then we can calculate a few things. Right, what was I going to say? So yeah, if you were thinking in the copper, the 3-band model of the copper-oxygen picture, in fact, there were several papers by Emery and Reiter in the very early days where they questioned the idea of a Zhang-Rice singlet and said, really, there's a spin-a-half charge E object that sits on the oxygen side. So this is very much the kind of state they were talking about. But in a modern language, I think the real issue is not whether you're 1-band or 3-band. They're, in some general sense, they have the same physics, although the microscopic parameters could be quite different. The issue is whether your charge carriers are holon spin-on bound states or just holon. So here we're assuming that every holon binds a spin-on. It's just an energetic question. If the energy is right, they'll do it. Or more precisely stated, we are assuming there aren't any other Dirac points or Fermi surfaces of gauge charged object. That the only Fermi surfaces present anywhere are of gauge neutral objects. That's the main assumption. Yes, they are. Yeah, that's really crucial to get the gauge structure. Yeah. So it has to be close packed. Otherwise, you don't get the gauge fields. Yeah. Yeah, that's a very naive way of thinking about it. Yes, but that's pretty reasonable. Yeah. Empty. Yeah. Yeah. Well, there could be 2 holes can form a bound state to form a Cooper pair, but then you would get superconductivity. Sure, but I want to describe a metal. So I want just a minimal model for a metal. So what I'm going to claim, the minimal model of the metal, the electron becomes a dimer. It's got a direction, and it sits on the bonds. And I'm going to play with this model. OK, so now you can actually define a Hamiltonian. You take this Hilbert space, and you define a Hamiltonian on it. In the old Roxar-Kivelson approach, there was just these 2 processes. There's a dimer exchange J and a repulsion V. And the famous RK point is the point J equals V, where you get equal superposition of all dimers as the exact ground state. But now we have other processes where this green can hop there, or these 2 can resonate this way, or you could get a Knight's move where the green can move over there. And there's a couple of others that we just left them out for simplicity. And in the limit, at least of large J over T, you can relate these couplings T1, T2, and T3 to the couplings, which I'll now call T, T prime, and T double prime of the TJ model. These are just come from nearest neighbor hopping terms of the TJ model. So we at least have rough estimates of what these should be. Okay. So that's the model we took. So what we've done so far is just take one green dimer and look at how it moves. What is its dispersion? Because if the green dimers are dilute enough and they're fermions, and they don't carry negate charge, then it's very reasonable to assume that once you dope the system, they're just going to form a Fermi surface at the lowest energy states. They're like hardcore fermions, which are moving in the sea of dimers. So, yes? Yeah. Yeah, so there can be spin exchange processes. I haven't even written them down. They're in our paper. Here, I'm only looking at a single green dimer on its own, right? It's moving around in the sea of blue dimers. But you can certainly have two green dimers and put it, so there's a zoo of extra interaction. I mean, the whole thing becomes out of control very quickly. So we're just trying to keep the very simplest things right now. All right, so in this very simple model, we've diagonalized up to 8 by 8 lattices, which involves 77 million states. Okay. Anyway, and in fact, for the parameters you get from the physical TJ model and the cuprates, this is the kind of dispersion you get, which has a minimum right over there along the diagonal, not too far from, well, these are discrete points, so it's near pi by 2, pi by 2. So you can imagine it can form so when you add a finite density of these, they'll form a little pocket over here. But what's much more interesting is we can also compute the quasi-particle residue. So now the green dimer is moving around, it needs to resonate with all the blue dimers. So it's not a bare electron. So it has a finite quasi-particle residue at all momenta, even with a single fermion, but it's not one. It's still quite non-trivial. It involves looking at the overlap of the wave function with and without a dimer. And so we can compute that overlap. And what you see about a wide range of parameters, that overlap is quite large here, but it dives down to very small values in the second Brillouin zone. Okay, so that's very encouraging because this can give you then a rationale for having large intensity on this side, but not on the other side. And we found this very robustly over a whole regime of parameters. Here's another regime chosen kind of randomly. You put everything equal to 1. As long as T2 is positive and larger than or equal to T1 and T3, this is the structure you get. And in fact, in the microscopic coupling, we do find T2 is the largest one and positive. There is no Fermi level. It's just one fermion. So now the assumption is when you put if the fermions are dilute enough, then all they're going to do is occupy these states. There's some with very little correction. But so most of the renormalization, the quasi-particle residue, is coming not from the interaction of the fermions with each other. It's coming from the fermion being renormalized by the gauge field, if you wish, by all the dimers. Well, no, so these are positively charged fermions. You create a whole pocket. This is a whole pocket, yeah. So you'd expect a whole pocket here. All right, so this, yes. Sorry? Yes, this would, correct. So we're actually working at the point J equals V, but yeah, it would be, right. So we're assuming that the confinement length scale is larger than the spacing between the fermions or something. As you know, you can make it a Z2 and all of that, but that's going to cost even more numerically to do all that. We're just doing the simplest thing right now. No, okay, this is just a bad choice of notations. I standardize this notation in all our computer files with us, and we stuck to it. But if you can see, it's actually T1 is this thing moving here, and T2 is just going here. It's in fact even going closer. But actually, the important reason you can see over here is in terms of the TJ model, T2 is T minus T prime, and this is T plus T prime, and you know that T prime has the opposite sign from T. So that's why it becomes larger. Well, so we believe in principle there's a mapping from the TJ model to the dimer model. Now, formally, we only know how to make that mapping in a certain large n limit, and also only for J much bigger than T. Okay, so we just take the first order term from that double expansion, and that's the answer. We just assume that's a reasonable guess. That's all. It's much harder to do. It'd be very, very hard to do anything better. What I'll say is that with all this, after all this mappings, we can diagnose an 8x8 system. Even though there's only one fermion, it's still got 64 electrons in there, or 63, and no one else can do that. So it's still a fairly large system you can do by all this guesswork on what are the important states in the Hilbert space. And this is on, it ran on this laptop. So, although it takes a few weeks. Running one right now. Okay, so that's been a lot of fun. Okay, so this was an earlier calculation based on some field theory of spin-ons. And, well, this was actually kind of a phenomenological, what happened there? No, the power was off, so my computer died. I hadn't turned that on. Yeah, now it's charging up. In high fields. And in high fields, it seems like this density wave order takes over and reconstruct the Fermi surface. So, right, so that's obviously the obvious solution. You want somehow to be able to detect the pocket at high temperatures. And it's a challenge. It's going to be much harder than the fractional quantum Hall state because the length scales are so much shorter here. You can't actually, but I think STM is starting to look at higher temperatures and high fields, and you can look at other systems which have much lower TCs.
But also, is it possible magnetic field can break that bond between spinon and holon? Is there any
well, that would also be very interesting, that if a magnetic field gave a spin liquid state with actual fractionalization. That's what many people hoped. So far, there's no sign of it. Yeah, that's the logic of the presentation today. Sorry? Yeah, so the T star line, as in Senthil's discussion, okay, this is our phase. So there's some QCP here, which we are describing in terms of a Higgs transition, and the T star line is somehow associated with that QCP. What we're talking about really things below T star over here. So this is the FL star I just talked about, and this bond density wave. Yeah, so this is beautiful pictures drawn by Devanjan.
So what happens to your weird Fermi thing as you cross over?
Yeah, well, that's what part I skipped. So I could talk about a little bit. I mean, sure. At the moment, I don't want to give a whole other talk. But roughly speaking, we want to go from an antiferromagnetic ordered state to a large Fermi surface state. And normally, the old Hertz-Millis picture, you just go directly from the antiferromagnet to the Fermi liquid. And we've certainly spent a lot of time worrying about that theory, and there's pretty good evidence that theory, there's in fact D-wave superconductivity as you go from a doped antiferromagnet to a Fermi liquid directly. But what we're proposing is kind of an indirect route. You go from here to there, and in between you meet two new phases. This is a phase with, these are both non-Fermi liquids and actually a spin gap, but we presume the spin gap is not too large. And one of them has small pockets, the other has large pockets. And then there's an analog of the Hertz-Millis transition, but it happens in a non-Fermi liquid. So one consequence of this transition here has no autoparameter. There's no broken symmetry, but it's It's in fact a Higgs transition, very much like the Higgs transition you might imagine the early universe for the weak interactions, which reconstructs this Fermi surface, these non-Fermi liquid Fermi surfaces. So that's the simplest route I know of connecting these two in an exotic way. There may be others, and this is what we've been working with. Yeah. Okay, first of all, there is an important issue of notation. What you call it's a d-density wave, unfortunately, means something else to many people. Okay, we call it a d-form. There's a d-density wave of Loeffler and Chakraborty, which is something completely different. And the reason it's different is because they screwed up on this factor of 2 in that exponent. But anyway, so what I've shown is that there is a natural connection, or at least between this this FL star metal, this fractionalized Fermi liquid metal, and this d-form factor density wave. Correct. Superconductivity may not be there, may not required at all. It could be. It seems like a difference. Yeah. Well, that. Right. Yeah. So this is the old picture that you start from a Fermi liquid. You start from a large Fermi surface, and you look at the particle-particle channel, and you get d-wave pairing. And if you look at the particle-hole channel, in this case, you do get also d-wave pairing, but at the wrong wave vector. That might seem like a trivial thing, but no matter how much I played with this and my students played with it, we couldn't get it to work. On the other hand, if you do the particle-hole channel from this Fermi surface, you get everything right for the density wave. Now you're asking, what about the particle-particle channel? Yeah, you do also get d-wave, but we haven't analyzed that as carefully. I mean, I think this is really designed for the metal at high temperatures. For the quantum diamond model picture, we would have to put in a few more states to get the d-wave. I mean, it's very easy to see from the quantum diamond model why you'll get d-wave pairing if you just add in also the bound state of 2 holons, as has been known for a long time. Yeah. So, but that calculation I haven't presented.
So I think we should break for tea, and we should thank the speaker for a lovely talk. And we will meet again at 11:25 here.